Okay, so hi everybody. So I'm going to start off with a recap of what we did last time. Okay, where we talked about SL3C and it started introducing these concepts of root system, roots, basically coming from simultaneous diagonalization. Okay, so there's a lot of data to remember here associated with SL3, but basically, if you understand this SL3 case, it'll give you some good insight into what's happening for general semi-simple Lie algebras. Okay, so here we're starting with SL3. Remember what that is: 3 by 3. The natural presentation is as 3 by 3 trace-free matrices. Okay, this is a simple Lie algebra. So it doesn't have any non-trivial ideals, just 0 and the full thing. If we want to study it, what we're going to do is we're going to so-called branch down to the diagonal matrices. We're going to consider the action of H, these trace-free diagonal matrices, also called the Cartan subalgebra, and let that act via the adjoint representation on G. So we're going to take this adjoint representation and basically restrict it to H. The nice feature that H has is that, well, you know, this is an abelian subalgebra. All of those elements commute with each other under the matrix commutator. Okay, but that has the effect that, well, we have this theorem from linear algebra that if you consider two endomorphisms that commute, they can be simultaneously diagonalized. Okay, so here we're really talking about the application of this representation to each of these elements. Okay, so so all of those simultaneously diagonalized. We're starting out just by considering the add representation. We'll talk about later on more general representations, but you have the same idea. You want simultaneous diagonalization. Okay, so from this, you get a more general notion of what an eigenvalue is. So here is just the eigenvalue equation. Okay, and this is the notion of an eigenspace. Well, actually not yet. This is, okay, so G alpha, we consider those x's that under the add H action, they just rescale that vector x. Okay, so this here, alpha of this input H, this is a number. This is, if this is non-trivial, this space is non-trivial, this would be called an eigenvalue. Okay, it's just now, this is, yeah, so alpha is a function on these inputs coming from the Cartan subalgebra, these diagonal matrices. Okay, so when this is non-zero, okay, and when alpha by convention is not the zero eigen value, okay, then we call this a root, and this is called the root system, the collection of all these guys. Okay, so these alphas now, these are functions. Okay, they're functions from where to where? They're functions from H into scalars, into C. Okay, but because add H is linear, then also this alpha is going to be linear. So this is a linear functional. Okay, so we're working this so-called dual space, H star. Okay, so this is an abstract space, and we're going to get more and more comfortable with this as we go along. Okay, but from this, we're doing this diagonalization process. Okay, so G under this action, it starts getting chopped up into different eigenspaces or so-called root spaces. Okay, so you have H, and then you have a bunch of these root spaces indexed by the root system. Okay, so let's be a bit concrete. Okay, so we worked out these computations explicitly last time. We have this diagonal element, okay, an arbitrary such diagonal element, but sorry, with the trace-free condition here. Okay, so some of these elements is 0. We let this act on a general SL3 matrix, and then we start cutting it up into these eigenspaces. Okay, so here's some examples. So this is going to be an eigenvector, also called a root vector. The corresponding root is this alpha 1 guy. Okay, I have to review what this is. The so-called simple roots are as follows. Alpha 1 is epsilon 1 minus epsilon 2. What are these epsilons? These are basic functionals that take as input H, okay, so something like this, and then it spits out the ith component. Okay, so alpha 1 evaluated on this H would give you H1 minus H2. Is that okay? Okay, so if I let this act on this vector is a matrix, okay, then it's going to rescale it. It's going to rescale it by alpha 1 applied to H. And that's what we just said was H1 minus H2. Okay. Similarly, you get these other ones. So E23, so that's a 1 in the 2, 3 position. Okay, so that's also a root vector. Okay, and alpha 2, which is epsilon 2 minus epsilon 3, is the corresponding eigenvalue or root. Okay, so this is the full list of these roots. Okay, so alpha 1, alpha 2, alpha 1 plus alpha 2, and then they're negatives, and these are the corresponding eigenvectors. Okay, root vectors. Okay, is that okay? Chopping up our space into these eigenspaces. Please jump in if you have any questions, okay? Okay, but H star is a bit at this point abstract, and we want a more clear picture about what's going on. Okay, in particular, yes, I mean we have this alpha 1 and alpha 2. H star is two-dimensional, and this is going to be a basis for it. But how should I picture this basis? Is it an orthogonal basis, for instance? Are they perpendicular to each other? Or is there some other non-trivial angle between them? Okay, well, what do I mean by angle? That has to come from somewhere. It has to come from some geometric concept, okay? And that's where this killing form is going to come in, okay? So the killing form on G is a symmetric bilinear form. Okay, for inputs X and Y from G, I have the corresponding add X and add Y maps. Okay, these are linear operators on G. So I could compose them and then take their trace. This gives me a number. Okay, so it's a symmetric bilinear form on G. And an important fact is that on semi-simple Lie algebras, in particular SL3, this guy is non-degenerate. And that's a key thing. Okay, so just like an inner product is non-degenerate. So this is what's going to give rise to geometry. Okay, so last time we ended off by computing what this is. Well, not in general. Like really, this is, you could evaluate this in a basis. G is 8-dimensional, so this would be represented by a symmetric 8x8 matrix. Okay, so we didn't work that out. What we need for getting going today and talking about the geometry of these roots is rather its restriction to H. Okay, so corresponding to these simple roots, I introduce the dual basis in H, right? These guys live in H star. The dual basis lives in H. Okay, so remember what dual basis means. These alpha i's, when you evaluate it on these ZJs, you get a Kronecker delta. A delta ij. So let's just check that. Epsilon minus epsilon 2 evaluated on this first one should give 1, while epsilon 1 evaluates to give me this one. So 2/3 minus 1/3. So that adds up to 1. If I evaluate this on the second one, well, these two values are the same, so I get a 0. Okay. Similarly, this on this gives you 0. This on this gives you 1. Okay, so in that basis, we take this, we evaluate these guys, right? And so we evaluate this matrix. Okay, it's a 2x2 matrix, okay, because there's 2 basis elements here. And so we found that this is the value, okay? And most important here is that this is non-degenerate. So I take the determinant, okay, and it's non-zero. So this is what's going to give rise to geometry, okay? So this is like it's like an inner product, but the small subtle detail is that this is not a real vector space. This is a complex vector space. Okay, we'll do some restriction to some real thing shortly, but it's something non-degenerate. So non-degenerate things, non-degenerate pairings like this, give me isomorphisms between a vector space and its dual. Okay, just by doing an insertion into the pairing. And conversely, so given any dual vector over here, you could represent it by some vector over here. So any covector can be written as you take this the pairing, insert some special vector H alpha. Okay. And finally, so once you have such non-degenerate forms, then you could induce corresponding pairings on the dual space, namely the pairing between alpha and beta. You take the corresponding vectors and pair them up. Okay. So you use this pairing over here. Whatever value you have there, that's what you define to be this. Okay. So there's some definitions to get through if you're not used to playing around with these dual spaces. But the most important thing, I guess, computationally, that makes things very easy that we worked out last time is that if you have the matrix representing this bilinear form on a vector space, then you take the dual basis in H star, then the corresponding matrices here are inverses of each other. Okay, so easy enough to take the inverse of a 2x2 matrix. Okay. If you work through the definitions, then these H alphas, you basically just take this dual basis and start, so multiply it with this Gij matrix that you get over here. And so you could work out these components. Okay. So before I continue, any questions? That is a lot of information. Okay. But most importantly right now is we have a pairing on H star. Okay, and that's going to give rise to distance and angles. Okay, so any questions before I continue? Okay, so
is it possible to get an answer of what phase or what phase to give us a geometry if the turbulence is 0?
Well, yeah, so I mean, you're going to have some null vectors, right, in particular. Vectors that pair to 0 in particular with every other vector, right? That's what being determined at 0 gives you. So but that's not the case for any semi-simple guys. So we have a theorem, Cartan's theorem, that tells you that for semi-simple guys, these are always non-degenerate. Okay, so let's start in on the root diagram of SL3. Okay, so the key idea here is that B introduces geometry on the space of roots. Okay, but rather, right, H star is this complex vector space, right? H is a complex vector space, so the dual space is a complex vector space. But remember, all the action, okay, so alpha 1 and alpha 2, they're these other roots, so alpha 1 plus alpha 2 and their negatives, right? We don't really need all of that complex vector space. We could just work inside a certain real slice, namely the real span of alpha 1 and alpha 2. Okay, this is a real two-dimensional vector space. Okay, so note that the root system, well, that's sitting even smaller. It's in the Z span of alpha 1 and alpha 2. Okay, so let's work in this real slice. And then, so if we take this real slice of this complex vector space and equip it with this non-degenerate pairing, right, that is going to be an honest inner product space that you're familiar with from first year linear algebra. So this guy is an inner product space. Okay. So actually, there are some details to check here, and it really comes from the fact that, well, we should take this form that we have here, okay, and check that it's positive definite, right? So really, I have to check what the eigenvalues of this are. Well, the 1/6 doesn't actually matter as far as determining whether this is positive definite or not, right? It's a positive number. Okay, so let's just get rid of this. Okay, so if I calculate what are the eigenvalues of this matrix, okay, then you'll find that the eigenvalues are, so use a characteristic equation. Okay, so we're going to just, oops. So check. So we want to take the determinant. So the determinant of this lambda 3. So this matrix is positive definite. Okay, that's what this is. Okay. So remember, this is the pairing on H star. Okay, so in the alpha 1, alpha 2 basis, this is what it looks like. Okay, so I'm asking the question, is this positive definite or not? And it doesn't matter this 1/6. So let's just forget about it. And then I do the eigenvalue equation for what's left, and I'm getting positive, strictly positive eigenvalues. So this is positive definite. Okay. So I am going to be getting an inner product space. Okay. This is, so we're going to be working here. Okay, so from this guy, so this from, remember, this matrix of inner products was this guy. So we have the following. Okay, so this first component is, well, 2 divided by 6 is 1/3. So we have alpha 1 with alpha 1, which is 1/3. That's the same thing as alpha 2, alpha 2. And we can also check that alpha 1 plus alpha 2 paired with itself, that's also 1/3. Right? So when we do that, we have to expand this. We expand it like, well, bilinearly. So this would be, right, alpha 1 plus alpha 2, alpha 1 is the same thing as alpha 1, alpha 2. So we have 2 of these guys. And then, oops, 1 of these guys. Okay, so this is 1/3. This is 1/3. And this is, what do we have? -1/6 times 2. This is -1/3. Okay, so we get 1/3. Okay, so all of these vectors, remember alpha 1, alpha 2, and alpha 1 plus alpha 2, these were positive roots. Okay, you also have their negatives, but this says that all of those roots have the same length, right? This is so this inner product of alpha 1 with itself is the length squared. Okay, so norm, remember, is the same thing as taking the inner product of a vector with itself. So therefore, these guys all have the same length, and they're 1/√3. Okay, so the next question that we ask is, well, how are they situated relative to each other? What's the angle between them? So then we just use the usual angle formula from high school here, right? So if theta is the angle between alpha 1 and alpha 2, then theta is, so cosine of theta is alpha 1, alpha 2. So they're dot product, right? You divide by the product of their lengths, and then you take the arc cosine to get the angle. Okay. So alpha 1 paired with alpha 2, again, that's part of the data that we have available to us at this stage, right? So alpha 1 paired with alpha 2 is minus 1/6. Okay, so we have arc cosine minus 1/6. And then we have this 1/3, sorry, 1/√3, but we have to take 2 of those guys, okay, or take a product. Oops. So we have arc cosine of -1/2. So what's the angle? The angle, again, from high school geometry, so that's 2 pi over 3. Okay, this is a key thing. Okay. So alpha 1 and alpha 2, they don't sit like this. This is not an orthogonal basis. Okay. But really, why should they be? That's something that we're used to. We like working with from first year linear algebra, but here, at least as far as what we're naturally led to, right, they're not the same. It's not 90 degrees. Alpha 1, alpha 2 is not orthogonal basis of H star. Okay. So similarly, I'll just write down the result. So we could calculate. So the angle between alpha 1 and writing alpha 1 plus alpha 2 is pi by 3. Alpha 1 and alpha 2 and alpha 1 plus alpha 2 is pi by 3. Okay. So now we can start drawing the picture. So the root diagram for SL3 looks as follows. Oh, sorry. Usually the one in the middle is drawn fatter. Okay, so that's the 0 base. Okay. Here's alpha 1. Here's alpha 2. Here's alpha 1 plus alpha 2. And then you have the negatives. Yeah. Okay, so you have this angle pi by 3, pi by 3, and all the way around. Okay. And these lengths, they're all supposed to be equal. Okay. So that's the root diagram of SL3. Okay. And it looks at this stage like it's just a small shell of the information that we started out with, right? But we'll see. Oh, well, we're going to even go further and compress this information even more. Okay. But we'll see that actually it really contains a lot of information. Okay. Any questions so far? Okay, so all of this is sitting inside this real two-dimensional vector space. Okay, we're working the plane. Okay, you have 6 points on the outside, and then 1 point in the middle. But these really play a different role. These play different roles. Okay, the ones on the outside, remember the eigenspace, the root space corresponding to it, is one-dimensional, whereas the one in the center, so this is not a root. This is the corresponding eigenspace is the Cartan subalgebra, the diagonal matrices, which is two-dimensional. Okay, so 6 dimensions on the outside, 2 dimensions on the inside. So that gives 8, which is the dimension of SL3. Okay. Okay, but now we have geometry to play around with. Okay. Okay, so a couple of observations here. So vector addition. Vector addition corresponds, so in the diagram, corresponds to the Lie brackets. I'll put this in quotations. So what I mean is that if I take the corresponding root spaces, G alpha and G beta, and I pair them using the bracket, then we're going to land in this other root space, G alpha plus beta. Actually, careful, because remember, this is not always a root space. It might be 0. It's only called a root space when this is non-zero. Okay. So first of all, let's show this. So where does this come from? It's just an application of Jacobi. Okay, so let E alpha be over here. So we're going to assume that alpha and beta, say, are roots. Okay, so E alpha is in there, and E beta. Okay, so these are my nice eigenvectors or root vectors. Then, okay, so we want to know, where does E alpha paired with E beta, where does it land? Okay, and since we're doing everything with respect to the Cartan subalgebra, to determine where this lands, I need to act with something in the Cartan subalgebra. Okay, so we're taking an H inside trace-free diagonal matrices. We're letting it act on this bracket. And so to evaluate this, we use Jacobi identity. Okay, so this add H map, it acts as a derivation. Okay, but now is where we use the eigenspace property, the root space property. So this guy is alpha of H times E alpha. Okay, and similarly, this is beta of H E beta. Okay, so this is a number, so I could just take this out of this bracket. So this is a number, I could take it out of the bracket. Okay, so what we're left with is alpha of H, E alpha, E beta, beta of H, E alpha, E beta. Okay, and collect this together. Okay, so right, alpha of H is a number, beta of H is a number. So I could write it as alpha plus beta of H, E alpha, E beta. Okay. So the conclusion here is that if I pair E alpha and E beta together, well, that result is satisfying the eigenvalue equation. So add H on that guy is, well, it's rescaled. Rescaled by what? Rescaled by this number. Okay, so therefore this is in this G alpha plus beta. Okay. Now this, where it lands, it might be 0. Okay, so there's two possibilities. Okay, so 1, alpha plus beta is not a root, is not a root, and it's not the 0. It's not the 0 element. So if you're in this case, then you know for sure that G alpha plus beta is 0. So therefore, E alpha, E beta would be 0. Okay, so is that okay? So you could read this information just from the structure, from the picture. So for instance, if I take something from here, like a root vector from this corresponding root space, okay, and I bracket it with something over here, corresponding root vector, well, that's definitely going to be 0, right? Because the vector addition of these two would land you over here, and this, that's not a root. It's not in the root diagram. Okay. So we know that these two elements, or rather, yeah, the corresponding. So I'm pointing to this picture in the dual space, but I'm really talking about the corresponding vectors. So this is a diagram. There's 6 points on the outside, and there's 1 point in the middle, right? So take this, add it as a vector. So this is a vector, okay, and this is a vector. Add them together. So I use vector addition, right? So I use parallel translation of this. I put it over here. So I'm getting to this vector over here. It's not in the diagram. So it's not a root, and it's not 0. So therefore, the corresponding roots, G alpha 1 minus alpha 2, that's 0. Okay. So you do get some structural information about brackets just from this picture. Yep. Sure, but it will not be a root.
No, but then you can see that that's none of the.
Sure. Sure. Yep. Yep. I think part of this is we don't always want to bring it back to the epsilons. Epsilons were introduced at the beginning, and that's really, these are weights adapted to the standard representation. Here we're talking about the adjoint representation. Okay, so I'm trying to get to the viewpoint that working in the alpha 1 or alpha 1, alpha 2 basis is better for certain things. Okay, but if you want to work things through from the definition to convince yourself, that's absolutely great. Yeah. Okay, but yeah. So the point I'm getting to right now is that, yeah, if you add this with this doesn't give you a root. Okay. So you know that the corresponding elements in the Lie algebra, root vectors, will commute. Okay.
But you can get some combination of alpha 1 and alpha 2 such that you get roots.
Yes, 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 yes. So the other possibility is that this is a root. So for instance, if this and this guy, well, this vector added with this vector will go over there, right? Of course, you might ask, there are two possible, well, that doesn't really guarantee, just because you have this vector addition working out and it is a dot in this diagram, is the corresponding bracket going to be 0 or non-zero? Okay, so there you really need a bit more information. Okay, it does turn out that if you take a root vector with, yeah, this one and this one, you will get a non-zero element. Okay, but that I haven't shown yet. Okay, but you can verify that. But so let me just write that down. Okay, so.
Wait, did you say that wasn't in the root? Then we found out it's not in the root space, the center of the diagram.
Which one?
If like if we take alpha 1 plus minus alpha 1.
Alpha 1.
By definition, when we had a.
Oh, this one and this one.
Yeah.
Yeah.
If we add them together, then we said before that we didn't want to include that in our root space.
That's right. That's right. So here I haven't declared that I'm talking about, like, this could be 0. So alpha plus beta could be a root. It could be 0. Okay. This artificial thing of this seemingly artificial thing. So just talking about roots and then separating out the 0 one. It's because these behave in a different manner. But as far as this formula is concerned, you can have this being equal to 0.
Yeah.
This alpha plus beta being equal to 0. Okay. In which case this bracket could be 0, could be non-zero. Okay. Okay, so well, okay, actually, so a priori, it seems alpha beta is okay. So you need more information. Let me leave it like that. Okay. Yeah, it does turn out that if you take something from here and here, like opposite sides, okay, then like along a line, then they will pair non-trivially. Okay, I'll give you this really concretely. Okay. Okay, so what I want to make a point out about right now is relating things back to SL2. Okay, so remember, what does SL2 look like? SL2, remember, you have eigenspaces associated with the adjoint action of SL2 on itself. What are the eigenvalues that kept coming up there? It was 2, 0, -2. Okay, so the root space decomposition for SL2, you'd have H, okay, and then you'd have the eigenspace corresponding to 2, and the eigenspace corresponding to -2. It's represented by 3 dots, okay? 3 dots all sitting collinearly. So in this diagram here, you see this in 3 different places, right? You have this line, you have this line, and you have this line. These are all SL2s. Okay, so recall from SL2 that adjoint rep has 2, 0, -2 as weights. Okay. Okay, so these are collinear. So the root diagram, we have 3 such strings of dots. Okay, and you have all these SL2 triples. Okay, so let me just write these out. Okay, you have the one in E alpha 1. Okay, and this is a root vector that we've seen before, E alpha 2. And E alpha 1 plus alpha 2. You have the corresponding negative root spaces. And then when you pair them together, you get the corresponding H. Okay, so I'll write this as sort of little h alpha 1. Okay. Little h alpha 2. Okay, so there's some details to check, some computations to check here. Okay. Okay, but basically what these look like, say the first one, you have SL3, which looks like this, right? And for the first one, basically you have zeros over here, and all the action is happening in this top block. Okay, so you have E12, that's a 1 in this position, and zeros elsewhere. You have E21, that's over here, and then you have 1, -1, that's your H. Okay, so that's the first one. Then you could have For the second one, right, so you're in all the actions happening in this bottom 2x2 block. For this other guy, I guess you have zeros over here. Okay, so 3 distinct SL2s appearing. Okay, so
Is this the line in the diagram?
Yep. So as in, so in the course, yeah, so in the corresponding root spaces, say, so over here, okay, so you have an X over here, namely E12, the corresponding eigenvector, okay? You have E21 over here. You bracket them together, you get the diagonal element 1, -1, and then 0. Okay, so that's an SL2. That's an SL2 triple. Okay. But it's predicted because you have this string of 3 dots. Okay.
How would you do dots for us?
Yeah, because remember, all SL2 representations are a string of dots, right? M plus 1 dots, that represents SMC2, right? Yeah. So, but for SL2, which is 3-dimensional, right? You have 3 dots. Yeah. Okay, all in a row. Yep.
So here you wrote some lines between the dots.
Yep.
Is there a reason why we don't write lines when with the SLP?
That's a good question. No, I guess that's I actually don't have to write these lines here. The lines are not really. I put it in there just because I'm putting an angle here, I guess.
Yeah.
Yeah.
Because of the angle.
Yeah. Otherwise, it's hard to picture. But maybe I'm just used to doing it. But really, yeah. The diagram, you're perfectly correct. The diagram is, strictly speaking, 6 dots and 1 fat dot in the middle. Okay, no lines in between.
How do we know that the dots is on the line in SLP? Can't we prove that the angle and
That's a good question. So I mean because we never talked about angles there, right? But really, yeah, so it's how you're picturing. In some sense, it's ingrained into how you're already used to thinking about numbers, right? Because 2 is positive, so we think, and -2 is negative, so we picture that on a line, right? So X, for me, I'm used to thinking, yeah, X moves, so positive things go to the right, negative things go to the left. Okay, and so this string of M dots that you're used to, you could, yeah, like we're laddering left or right, depending on whether it's positive or negative. Yeah, it's just numbers. No, we're working in the plane. Yeah, so we have to think about vectors. Well, that's a really good question. Yeah.
Is the coton, does it have a coton subalgebra in the SL2 case as well? Can we look at?
Yeah, it's the span
That's
of
one-dimensional.
H,
Yeah,
and it's
that's
one-dimensional. Yeah,
Yeah.
exactly.
Maybe that's the.
So in some sense, SL2, it's nice and we fleshed out all the details, but in some sense, for the general theory, it's a little bit too trivial.
Yeah.
Okay. But it's essential because, as you see, SL2 is embedded everywhere. Yep. Yep.
So then in the diagram, if you go up to higher dimensions, we sort of add another dimension.
Lots of SL2s. Yeah. But in some sense, some of these SL2s are a bit more fundamental than others, right? So I introduced alpha 1 and alpha 2. There's also this other one, alpha 1 plus alpha 2. But alpha 1 and alpha 2, they're forming a so-called simple root basis. It's nicer in some sense. I could have chosen alpha 1 and this alpha 1 plus alpha 2 as the basis. But actually, it's not so nice. But for various reasons that we'll get to, not today or tomorrow, but I'll describe next week. Okay. All right. So let's flesh out a few more details. Okay. So definition. Given alpha a root, remember you had this killing form that allows you to get for a covector here, then the corresponding vector. Okay, we denoted that by capital H alpha. Okay, so we use the pairing, the killing form. Okay, but it turns out that if you rescale it appropriately, you're always going to get to an H from an SL2 triple. Okay, just like what we have over here. Okay, so there's some checks that again need to be done here. Okay, but it turns out that this always works. Okay, so this is the H in the sense that we were using before inside an SL2 triple. And okay, so this is something inside the Cartan subalgebra. Okay. So there's something called the co-root, okay, which is alpha, and then you rescale it by the same amount. Okay. Okay, this notation is very useful. It's going to come out again when we talk about Cartan matrix. It's going to come up when we talk about the Weil group and reflections. You're going to see these factors continually pop up. So this is just a shorthand notation for that. Okay, so this one? This is for any root. It could be alpha 1. It could be. What is this capital H? Yeah. Okay. So I said that before, but let me just remind you. So remember you have this isomorphism between H and H dual. Okay. And it's induced by this pairing that we have, like an inner product. Okay. So if I have an element alpha here, I have a corresponding element over here. Okay, and it's via the pairing. Okay, so alpha is you take the pairing and then you insert some special vector H alpha into it. Okay. Okay, so really the point is just you're doing some non-trivial scaling to get some nice H, right? Because we had so much focus on that in the SL2, so we want to bring those out and see how they act. Okay. So we do this non-trivial rescaling here and then get the corresponding non-trivial rescaling over here so that under this sharp map, okay, sending from H star to H, these correspond. Okay.
To the power, alpha to the power V.
It's this check thing. Yeah.
Check.
Yeah. Okay, so if you do that for these alpha 1, alpha 2, and alpha 1 plus alpha 2, you will get these little h's over here. Okay. Okay. Maybe go. Actually, let's take a break here. I think that's probably good. Yeah. Maybe 10 minutes. Yeah. Okay. Okay, so let's continue. So we're going to talk about Cartan matrices now. Oops. Okay, so we saw before the root diagram, but we're going to actually compress that information even more to the so-called Cartan matrix and Dynkin diagram. Okay, so let me give you the Dynkin diagrams. Okay, so these are extremely important objects as we go along with the theory. Okay, so the Cartan matrix is the matrix with entries Cij. given as follows. Okay, so Cij is going to be take the pairing of alpha I, the simple root alpha I, with alpha j, but not just alpha j. We're going to do check on this, the co-root. Okay, so reminder about the definition of co-root. You're supposed to, okay, so I'll just rewrite this. So what is alpha j check? I'm supposed to take alpha j and then multiply by 2 and then divide by alpha j, alpha j. Okay, this is a little bit messy writing out like that. So we're going to write it out instead. Okay, well, we'll pull those factors out. Okay, so 2 alpha I, alpha j, and then divided by alpha j, alpha j. Okay, so these ij indices range over the simple roots. Okay, so for SL3, we have two simple roots. This is going to be a 2 by 2 matrix. But how this is defined, from how this is defined, right, with this alpha j in the bottom, Cartan matrices in general, so beyond SL3, are not necessarily symmetric. Okay. In the case of SL3, it will be a symmetric matrix. Okay, I'll state what that symmetric matrix is. Okay. Other conventions. So here, when I write it Cij, I take as the row index and j as the column index. That's not always consistent in the literature. Sometimes it's transposed. Okay. Other things. So since, okay, so that's the definition. Since, well, if you take j to be equal to I, then you're going to get 2. So on the diagonal, you're always going to have 2. So 2's on the diagonal. For SL3, what does this look like? So for SL3, it's 2 minus 1 minus 1, 2. Okay. This is extremely important information, so I'm going to put that highlighted. Why is that? So we know about the 2's on the diagonal. So let's recall. So since, well, C12 is 2 alpha 1 alpha 2 over alpha 2 alpha 2. And then we have that matrix from before, right? It was, right, we actually had this. So previously we had this 1/6 2 minus 1 minus 1 2 as this alpha I alpha j matrix. Okay, so we have let's see, 2 times minus 1 over 6 over 1/3. Okay, so this is minus 1. And similarly for C21. Okay. It's clear that C21 is equal to C12 because we already showed that alpha 2 is the same thing as alpha 1, right? These roots have the same length. Okay, so just as a warning, C is symmetric for the SL series. Okay, we'll see that later. But not necessarily more generally. So, for example, for SO5C, okay, here's a Cartan matrix. So 2's on the diagonal, 0's over there, minus 2 over here, minus 1 over here. And it is going to be a general fact that on the diagonal, well, we saw on the diagonal, it's always 2. Off the diagonal, it's always going to be non-positive. But moreover, C is always Z-valued, okay? Actually, it's even tighter than that. Basically, off the diagonal, you're going to only see the values 0, -1, -2, or -3, okay? So this is, in fact, what's going to lead to our ability to classify simple Lie algebras later on, okay? But we'll see some more of this next week, okay? For the moment, it's just a definition, okay? This Cartan matrix that's, okay, we have this inner product on the top, we have this inner product on the bottom, but that definition allows the following observation. So most importantly, for now, C is independent of rescaling this pairing, okay? So remember how I said this morning that, how we discussed that the killing form is distinguished in that it's invariant under automorphisms, but of course, that condition is a linear condition. So if I rescale it by 10,000, that's also a form that's invariant under automorphisms. So choosing this definition of the killing form to use as defining geometry, that's not distinguished. I could always rescale, okay? But now, in taking this definition of Cartan matrix here, you've eliminated having to make that choice, right? If I rescale this and I rescale this at the same time by the same amount, I'm using the same inner product, that scaling cancels itself out, right? So it's good to be aware of choices that you make and objects that are independent of these choices. So that suggests that the Cij is something important, okay? Okay, so let's, just as I said before that B, this killing form, introduces geometry on the space of roots, the conformal class, so if I, instead of having to make a choice, let's just take all those rescaling choices. So the conformal class okay, so of all possible rescalings of the killing form, okay, introduces conformal geometry. Okay, that just means that, well, I mean, we're used to talking about an inner product that defines a notion of distance, right? And you get angles as a derived concept, right? But here, by rescaling, the notion of distance loses meaning, but the notion of angle does not. Okay, so conformal geometry is the geometry of angles, not metric distances. Okay, so angles and, well, relative lengths. Okay, so for example, if I consider the ratio, that'll still have some intrinsic meaning, okay, independent of the choice of whether I choose B or 10,000 B, right? So these concepts persist as having meaning in conformal geometry. Okay.
What's conformal geometry?
Basically, instead of considering an inner product, I'm considering all rescalings of that inner product.
Okay, so just what you've defined.
Just what I've said. Yeah. Okay. So, okay. So, we're really talking about conformal geometry in the background here. Okay. Nope, that's why they have different names. So, okay, so now let's compress the data even more. Okay, so here I'll give you a general definition of this Dinkin diagram. Okay, so the Cartan matrix is encoded via the Dinkin diagram. Okay. Who, by the way, Dinkin, I think he came up with this when he was an undergrad student, which is pretty amazing. Okay. But
No pressure on us.
no pressure, guys. Node I, so it's a graph, okay? So node I corresponds to the simple root alpha I. We're going to put a bond, a connection. So a bond of multiplicity Cij, Cji between nodes I and J. Of course, you'd be correct in asking the question, okay, does this actually make sense? Right? Well, I've told you, without proving it, that Cij is integer valued, and that off the diagonal, so when I is not equal to j, then it's actually negative. Okay, so this is going to be a non-positive. Okay, so this is going to be a non-negative integer. Okay, possibly there's no connection. If this is 0, then you don't put a bond. Okay. If alpha I and alpha j have different lengths, we're going to direct this bond from the longer to the shorter root. Okay. So the Dinkin diagram of SL3 is the following. You have two nodes, and then you have a bond between them, right? Because C12, C21, C12 and C21 were both -1. So their product is 1. Okay. Some examples of other Dinkin diagram examples. Okay. Oops. Okay, so this is another, yeah, in Cartan's classification, this is also called A2. The 2 denoting the rank of the Cartan subalgebra. This one is called B2. Okay, again, it's going to be rank 2. In more familiar language, this is SO5. The orthogonal algebra on a 5-dimensional vector space. This is C2. This is the so-called symplectic Lie algebra. Here's my favorite. This one's called G2. Okay. So these are, these 4 are the simple Lie algebras of rank 2. Okay. In fact, these guys, I mean, this looks very similar to this. It's just this is pointing in the opposite direction. There is actually an isomorphism between these two. Okay, in this particular rank, these are actually the same up to isomorphism. If you go to higher SOs, then these are part of a different series. You have the orthogonal series, you have the symplectic series. Those are different. And we'll see what those higher rank Lie algebras look like as far as their Dinkin diagram is concerned. Yep.
Can you just quickly go through the construction, like using the roots and the construction?
Yeah, sure.
of these, so we can,
Yep, sure. So node I corresponds to the simple root alpha I. So this one is alpha 1. This is alpha 2. Put a bond of multiplicity Cij, Cji. So here's just C1, 2, C2, 1. So we're putting a single bond. Okay. If alpha I and alpha j have different lengths, so that doesn't apply to SL3. They have the same length. So here, in this case, this C1, 2 times C2, 1 will give you 2. In this case, it will give 3. Okay. But in these cases, you have different lengths for those simple roots. Okay, so we'll see what those root diagrams look like next week. Okay, but yeah. Sorry, equal where?
B2 equals.
That's, you can take that as a definition. Yeah, definition. Yeah, yeah. But really, the subscript means something here. This means the rank of the Lie algebra. So there is going to be a Cartan subalgebra for these guys. In a certain presentation, it corresponds to diagonal matrices. Okay, but they're more restricted. Just like in the case that we've been considering, these are trace-free diagonal matrices. In these more restricted settings, again, the Cartan subalgebra is more restricted. There's additional conditions. Okay. Yep. It doesn't, but relative to lengths, it does. Because, right? So here, so I'm rescaling this length at the same time as simultaneously I'm rescaling this at the same time. So the scaling factor cancels. Yep. Mm-hmm. Yep. So the formula for angles, right? You have an inner product on the top and you have two norms at the bottom. Right. So the inner product, let's say it scales by lambda squared. Okay. In the bottom, you have a norm, so it will scale by lambda and lambda. So the scalings cancel.
Why are we now only consider alpha 1 and alpha 2 and not the alpha 1 plus alpha 2? Why is that?
Well, it seems like magic, right?
Huh?
It seems like magic. I mean, it seems like just a very, very small part of information of the original Lie algebra. And so that's actually leading to my next point. What's remarkable is that this information right here, it completely classifies the Lie algebra. Everything about it can be reconstructed from this information. That's beautiful. Absolutely remarkable result. So fact, rather, it's a theorem. So the Dinkin diagram of G completely encodes G up to isomorphism. As in, from this information, okay, I will be able to write down an actual, there's a process to actually write down a Lie algebra with commutators, like in a basis. And it will be isomorphic to the one that you started out with. So say, yeah. So starting out with this, I will be able to reproduce this. Okay, so that's something called, there's a theorem called the Serre theorem, and so-called Serre relations. So we'll see, I'll formulate that later. Okay, but this is where we're heading. So yeah, today and tomorrow, it's all about two dots and a line. How hard could that be? Okay, yeah, Pao.
Does it work the other way around? Like any diagram that you can make up using nodes, multiple examples?
No, so there's compatibility rules, and so that's exactly, so understanding what these rules are, that's part of the classification problem. So I'm not sure if I'll be able to describe that in complete detail. Time is a bit limited, but I can certainly sketch some of the ideas. Yeah, we'll see. Okay, yeah. Go.
You said earlier that there were two that were isomorphic, the
Yep.
B2 and
Yep.
C2.
Yep.
So you can have different thinking diagrams.
Yep.
But they may still be isomorphic. or? was that-
Yes. So another example of this is, so like, this is SL4, which is A3. This is D3, which is SO6C. So I should have SL4C. It's basically graph isomorphism indicates Lie algebra isomorphism. I mean, it's awesome.
Yeah.
Right? It's awesome. There's no other, I mean, it's fantastic. Right. So I mean, I had during my postdoc, I had the chance to spend some time with this guy, Mike Eastwood in Australia, and he's like a master of this stuff. He's like, call him a Dinkin diagram whisperer. So and he just uses, so basically this is a compression of a beautiful and really complicated structure. Okay. So anything, like if you could prove theorems at this level, they have a lot of impact. Okay, there's a lot of meaning behind this. So I mean, I work in parabolic geometry. You start putting extra ornamentation on these Dinkin diagrams, like crosses or diamonds or boxes. I mean, there's some really cool things that could be read off from here. Okay, like cohomology and all these fancy words. Yeah, symmetry gaps. You just have to be able to know how to read this. Okay. To most other people, this looks like black magic. So, but yes, I will teach you some black magic. Okay, so on we go. Not so much black magic today. So we'll see. Weights. Okay, so we want to do a similar thing that we did for the adjoint representation. Now for any representation of SL3 or SLN semi-simple guys, right? So same idea. So we have this guy. Oops. Okay, this is SL. Basically, all the things I'm talking about today can generalize from SL3 to SLN+1. Okay, and so we have our H sitting inside here, and key idea, simultaneous diagonalization of pi of H. Okay. Okay, so you want to simultaneously diagonalize. Okay, so instead of talking about roots, now we're going to talk about weights. Okay, similar idea, eigenvalues. So given an element of the dual, define V mu as those vectors that when you apply one of these linear operators, pi of H, where H comes from the Cartan subalgebra, then it acts as a scaling. Okay, so my scalar here is mu of H. Okay, I shove the H into this functional. That's a number. And here we're doing an arbitrary choice of element H from the Cartan subalgebra. Okay. We know this makes sense because of this simultaneous diagonalization idea. Okay, and so if this is non-zero, then mu is a weight. Okay, and any element from V mu, any non-zero element from V mu is a weight vector. And V mu is the weight space. Okay, so similar ideas as before. Rather with, let's put in multiplicity. Okay, with multiplicity being the dimension. Okay. So this is multiplicity in the sense of geometric multiplicity, okay, in the linear algebra sense. Okay. So just to make sure you're not confused with roots and weights. So roots is in the setting of the adjoint representation. Okay, so when V is equal to G, non-zero weights are called roots. Okay, so we already saw. So 0 is a weight. But by convention, it's not a root. Okay. Every SL n plus 1 C rep has at least one weight. Okay, why? So given an element of the Cartan subalgebra, I could I could consider pi of h. That's a linear operator, but we're working over C. Okay, so a linear operator over C, like one linear operator over C, it always has an eigenvalue. Okay, so this is, you could rely on the Jordan theorem, say, for this. Okay. Or rather, not, it doesn't even have to be the Jordan theorem. Just you have a linear operator, you have its characteristic polynomial, right? And over C, it has a root. Okay, so you have an eigenvalue. So that's for one element from H, but then you simultaneously diagonalize, right? So you will get a non-trivial eigenspace. Okay. So let's build up our vocabulary of some basic irreducible representations, just like we did for SL2. Okay, so remember there, of course, there's the trivial representation. One-dimensional, doesn't do anything. But then we started with the standard representation. Okay, so example. So the standard representation. Okay, so what are the weights in this case? Let V be C3 and pi from SL3 to GL of your vector space. Okay, be the standard rep. Okay. We'll take usual basis E1, E2, E3. So you can take a general vector and represent it in column notation with respect to that basis, E1, E2, E3, right? So what does this representation look like? It takes as input, well, I want to restrict it to H, right? That's how weights are being produced. We want to look at the action of something from the Cartan subalgebra. Okay, so let's take a diagonal matrix. And let it act on a vector. Okay, I'm writing everything out in a basis. Okay, so this pi with this input matrix from the Cartan subalgebra, it acts on this column vector. Okay, how does it act? Well, just in the obvious way. Okay, you just regard it as a 3x3 matrix. Let it act on A, B, C. And so you have H1A, H2B, H3C. Okay. So from this formula, this output formula right here, we get now a list of weight vectors and their corresponding weights. Namely, E1, E2, and E3, this basis that we started out with, right? These are actually weight vectors. Why? Because E1 is 1, 0, 0. What does this do to 1, 0, 0? You get H1, 0, 0. So that vector just got rescaled. Okay. What is the eigenvalue? It's H1. That's the application of this epsilon 1 to H. Okay, so the corresponding weights are epsilon 1, epsilon 2, epsilon 3. Okay. So if I don't write it out in a basis, right, so what we just calculated was pi of H applied to EI is HI but that's the same thing as this epsilon I applied to H multiplied by EI. Okay. So there's my eigenvalue, and it's produced by this functional epsilon I. Is that okay? Okay, and here I'm not using Einstein's summation convention. There's no sum here. Okay. Okay, so that's one basic representation. So let's look at its dual. So the dual standard rep. So given.
Can I just?
Yep.
The epsilon I, that's a linear function of taking in H, mapping it to the I.
HI. Yep.
Projection to the I form.
Yep. So given the above, we get pi star, which is the dual representation. So we want to write this out. Okay. So take dual basis to that E1, E2, E3. Okay, so this with superscript indices, E upper I paired with E lower j is going to be a Kronecker delta. Okay, delta ij. So, and again, let's take this in a basis. So let's A E1 plus B E2 plus C E3, so be an element of the dual space. Okay, so A, B, C, but now with respect to different bases, E1, E2, E3 with superscripts. Okay, so what is pi star? Now applied to ABC, but remember this ABC now has a different meaning than in the first example. This is with respect to this dual basis. So how does this pi star look in this dual basis? Okay, so what does it do to this matrix input? The action is via the negative transpose. Okay, so this is minus. Well, the transpose isn't going to do anything to a diagonal matrix, but let's just put it in there just to be safe. Okay, and so what we're getting is the output is minus H1A minus H2B minus H3C. Okay, so again, we could give our classification of weight vectors and the corresponding weights. Okay, so here the dual basis elements are the weight vectors. What are the corresponding weights? Minus epsilon 1, minus epsilon 2, minus epsilon 3. Okay. So this already, an immediate observation is that the weights are different from the standard and the dual standard. Okay, so that's different than in the SL2 case, right? In the SL2 case, C2 and C2 dual were actually isomorphic. We found this intertwiner between them. Okay, so that's not the case for SL3. Okay, so morning. So unlike for SL2, the standard and dual standard SL3 reps are not isomorphic. Okay. Okay, little exercise. Show that these guys are actually irreducible. Okay. Now let's make some parallels to the SL2 case, going off of the Cartan subalgebra. Okay, what about other root vectors? Okay, so like the analog of the X or the Y, these raising operators. Okay, so like for SL2, root vectors induce a weight shift. Okay, remember that X induces a weight shift by +2, Y induces a weight shift by -2. Okay, how do we show this in general? And this is really not restricted to SL3. Okay, so the lemma. Let's take a root vector. Okay, maybe these are negative roots, maybe these are positive roots. We haven't made that choice, it doesn't matter. Okay, these are from the Lie algebra, and we're going to let it act on something in the weight space V mu. Then, okay, so I'm going to let it act on this vector. Where is it going to live? Well, it's also going to be in a weight space. Well, it could be 0, but otherwise, if it's not 0, then it's in a weight space with this weight shift. So mu plus alpha. It's just, yeah, different from the SL2 case where we talk about numbers, right? Shifting by +2 or -2. Here we're shifting by a weight, okay? By the weight alpha. Okay. So this could be 0 or it's a weight vector. The proof is a one-liner. Okay, so we want to know that this guy lives in this weight space. What does it mean to live in a weight space? You need to know what the action of H is. So I'm going to take that vector and hit it with this pi of H. Okay, but we've seen this type of computation before. We do an interchange at the cost of a bracket. Okay. Really, I guess I skipped a step here. So this minus this would give you a commutator of, so the commutator of pi of H and pi of E alpha. I've used the homomorphism condition to write it like this, so that I could bring in the eigenvalue condition, okay? Because this is alpha of H, E alpha. This is a number. This is a linear operator. I can move that out. Okay. Let's see. Oh, that's right. I actually wanted to do this over here as well. Mu of H, because pi of H acts on V. V is a weight vector with weight mu. So I have mu of H times V. Oops. Again, this is a number, so I can move it past this linear operator. Okay, so we have mu of H pi E alpha V. And this is a number, this is a number. Let's just collect those numbers together and rewrite. So that's a number. Like that. And then we're done. Okay. This tells us that this will live in V mu plus alpha. Is that okay? Questions on that? Okay, so that's weights in general, and then two examples, the standard and dual standard representations, irreducible representations. Let's talk about fundamental weights. Okay, so the simple root basis that we chose before, okay, so that's convenient for expressing roots. Okay, here, so that's working in the adjoint representation. Okay, in more general representations, what we're going to do is we're going to use a different basis. Okay, yet another basis. Okay, but this one is very convenient to work in for various reasons that we'll get to later. Okay, so the fundamental weights, I'll denote it by these lambdas. So lambda I, okay, these are defined via this killing form, or the pairing induced by the killing form. Okay, so I want to take alpha j, but actually it's co-root. Okay, you'll see why this co-root introduction here is convenient later on. Okay, so we have a Kronecker delta. Let's get a different color here. Okay. Okay, so exercise show from this definition that just like the alpha i's are basis, show that this is also a basis for H star. Okay. Second exercise is for SL3. Verify for the, well, how to make this change from the, actually this, I guess this information will be later on. Let's see, I guess, no, okay. So let's actually postpone this exercise. Actually, let me just, since I started writing it, I'll just write it out, but I'll probably move this around. Okay, so these epsilons are all weights. I could write them out in terms of the alphas or the lambdas. Okay, and this is what they happen to look like. Okay, so first thing we need to know how to do is convert between them. Okay, so what's the change of basis? Because we are actually going to be using both of them for various reasons. Okay, so let's first of all, let's call this the alpha basis, and let's call this the lambda basis. Okay, so now recall we had this important matrix called the Cartan matrix. Okay, so let's define its inverse with upper indices. Okay, so Cij is C lower ij inverse. So the claim is that the transpose of C is the transition matrix. Okay, it's the change of basis matrix from the alpha basis to the lambda basis. Okay, and again, this is a short argument, so let's just use some definitions here. So alpha I is Cij lambda j. Okay, so here there should really be a sum. Okay, Actually, just because, yeah, otherwise I'm writing sums all the time. So I'm going to use Einstein's summation convention. Okay, so sum on J here. And going backwards, so from lambda I, you can write this out in terms of the alpha j's using the inverse. Okay, so we want to show this this first statement here. Okay. Okay, so an exercise that I just mentioned was that they both give bases. So you can write out, so by the exercise above, alpha I is some linear combination. Let's put a case here, actually. Of the lambdas. Okay. You don't know what the t's are yet. We'll calculate it in just a second. So let's use the definition of Cartan matrix. Alpha I paired with alpha j, check. Let's use this definition over here. So we have the t's that are numbers, so we could pull it out of the bilinear form. So tik, lambda k, alpha j, check. But we just had a definition that says that this is a Kronecker delta. Okay. There's a summation over k here. Okay. I'm summing and I have a Kronecker delta, so that means you only have a non-zero contribution when k is equal to j. In that case, this is 1. So this is Tij. And so we're done. Okay.
Why the transition
With upper indices?
da Einstein summation usually you from covariant and
I know. Old habits are hard to break sometimes.
Oh.
Yeah. Well, but we have a pairing, right? So, you know, there is a mix up or down, like there's an isomorphism there. So, yeah. But strictly speaking, you're right. Yes, I agree. Okay, so let's just write out this explicitly for alphas for the SL3 case. I'll make a couple of observations and we'll take a break. Okay? So, example for SL3. Okay, remember that we had computed 2 minus 1 minus 1, 2. Okay, so this is for the Cartan matrix. Remember, originally when we were doing the pairing between alpha I and alpha j, there was this factor of 1/6. We don't care about the 1/6, right? Yeah, we're using the Cartan matrix now. Okay, you get its inverse. You get that. Here it's you don't want to get rid of the 1/3. that is important. Okay, so by our lemma, we now write it out. Okay, so alpha I is Cij lambda j. So for alpha 1, I look in the first row. So 2 and minus 1. These are the coefficients with respect to the lambda basis. Okay, so this is 2 lambda 1 minus lambda 2. Alpha 2 is minus lambda 1 plus 2 lambda 2. Going backwards, I use the inverse Cartan matrix. So lambda 1, I look in the first row of the inverse Cartan matrix. Okay, so I have this with this scaling. So we have 2/3 alpha 1 plus 1/3 alpha 2. Lambda 2, you look in the second row. 1/3 alpha 1, 2/3 alpha 2. Okay. So of course, inside that H star plane, or H star real copy plane, which is two-dimensional, you could ask, where are these lambdas? How do they look? Where are they? And I'll draw those later. But just from these formulas, you could confirm a few facts. Okay, so confirm that alpha 1, lambda 1, lambda 2, alpha 2 are collinear. This is not necessarily going to be a true thing in other simple Lie algebras. Okay, but for SL3, this is true. Lambda 1 is perpendicular to alpha 2. We know that from this definition, actually, here, right? Lambda I with alpha j. So if j and I are distinct, then this is 0. So lambda 1 is going to be perpendicular to alpha 2. Lambda 2 is going to be perpendicular to alpha 1.
What do you mean by collinear?
They're all on a single line. Yep. You can use the pairing on alpha 1 and alpha 2 that we know written out in alpha 1 and alpha 2 language to figure out what the inner products, what the values of the pairing are on lambda 1 and lambda 2. Okay, so this length of lambda 1 is the same as the length of lambda 2. And that's 1 over square root of 3 times the length of alpha 1. Okay, so a little bit about the geometry to fill in, some little exercises here. Lastly, the highest weight of the adjoint representation, right? We've been talking about standard and dual standard. So what about the adjoint representation? So remember, in alpha language, this was alpha 1 plus alpha 2. So in lambda language, it's actually the same thing as lambda 1 plus lambda 2. Okay. So we're going to get to talking about highest weights shortly. Okay, but for the adjoint representation, this lambda 1 plus lambda 2, equivalently stated alpha 1 plus alpha 2, this is going to be our highest. Okay. Lastly, this transition matrix allows us to convert components from one basis to the other. So if I have a linear combination mi alpha I could make substitution of alpha I as Cij lambda j. Okay, so you're converting these mi components in one basis to these new components in the new basis. Okay, and I'll just write it out. So Ri lambda I is Ri Cij alpha j. Okay, so components in the alpha basis, you multiply by the Cartan matrix. But yeah, careful, this multiplication, so you think of the m's as a row vector, and then matrix multiplication with this Cartan matrix. Yeah, usually we think of components as column vectors, but here, yeah, I was careful to mention that the transition matrix is it's actually the transpose of the Cartan matrix. So there's some funny business going on there. Okay, so for example, let's see. So 2 alpha 1 plus alpha 2 has components 2, 1 in alpha land. So in the lambda basis, so I'm taking components regarded as a row matrix, a row vector, rather, multiplied by the Cartan matrix on the right. Okay, so this is going to give me 3, 0. So therefore, 2 alpha 1 plus alpha 2 is 3 lambda 1. Okay. All right, so a little bit of linear algebra there, different bases. I haven't shown you what we're going to use these fundamental weights for, but it will be related to these standard and dual standard representations. Okay. Okay, so let's continue. So next topic is integral lattices. Okay, and we'll see where these. Well, actually, before I forget, yeah. So the oops. So we talked about these fundamental weights. Okay, so it will turn out that once we define this notion of highest, that lambda 1 is the highest weight of the standard representation, and lambda 2 is the highest weight of the dual standard representation. Okay, and this will connect with also the Dinkin diagram language that, yeah, working in this lambda basis. Okay, so lambda 1 is 1 times lambda 1 plus 0 lambda 2. So this will be the highest weight for the standard representation. This will be the dual, a standard representation. Okay, so that's where we're headed. We have to articulate this a bit more. Okay, so let's talk about integral lattices. All right. So question. Which weights can appear in a representation? Okay. And always be working with like G being SL or yeah, SL3 or SLN at this point. Okay, semi-simple in general. Okay, so suppose V mu is a weight space. Are there any restrictions on mu? Okay. Let's take a non-zero weight vector. Okay. So what do we have? What we're going to do is we're going to take one of these H's, but of a specific form. Okay. So remember, this is one of the H's. Well, this is an H in a certain SL2 triple. Okay. By construction, there was some rescaling involved, right? So this is going to act as, well, little v lives in this mu, v mu weight space. Okay, so the action of this element from the Cartan subalgebra is a rescaling by a certain number. What number? Mu evaluated on this particular H. Okay. But what is this? I have a dual element evaluated on a certain vector. Okay. This is actually the same thing as you pair mu with the corresponding element here. Okay, so this is the so-called well, this is the element corresponding to this guy. Okay, so actually let me write it over here. So whoops. Since H alpha J is the sharp of this guy. Okay, so there are some definitions to get through. Okay, but if you go back, everything's consistent here. Okay, so this is a number, so we need to multiply it against the vector. Okay, so the scalar that comes out front is this number over here. Oops. With this co-root coming into play. So the key observation now. So each H alpha J is the H of an SL2 triple. So, but we know what the weights of appearing in SL2 representations are, right? These are all integer valued, okay? So a priori, we don't know anything about this beforehand. I mean, this could even be a complex number, okay? But because this is an H of an SL2 triple, it's highly restricted. So from our knowledge of SL2 weights, we have the key observation that this pairing, okay, so mu paired with this alpha J check, this is integral. Okay. Okay, we say such mu is integral. Okay, so you might be a little confused with this co-root, but let me just make it really concrete here. So concretely, if mu is, so we're going to use the lambda basis, okay? So what is this saying about, yeah, what is this condition saying in terms of these coefficients, these R's? So mu paired with alpha J check is, okay, see this Ri lambda alpha J check, and there's a delta Ij. Summation over I, so this just becomes Rj. So working in the lambda basis, we get this nice condition coming out on the coefficients of this weight expanded in the lambda basis. Okay, namely that these weights that can arise in practice in actual representations, these coefficients have to be integers. Okay. Okay, so this integer property, this integral property, rather, motivates us to, okay, we don't have to consider all weights, all elements of H star. We could just consider those that lie on a certain lattice, okay, an integral lattice. We know that lambda 1 and lambda 2, right, are important. Well, I guess at this stage, I just given them a name, fundamental weights, right? But I have told you that they do arise, like those ones do correspond to the standard and dual standard representations. So those definitely arise. So let's take the Z span of these guys. So that's the weight lattice. The weight lattice is it's the Z span, okay, of the fundamental weights. Okay, so that's living in this real slice of H star. So that's adapted to any general representation. So weights will live on the weight lattice. Okay, roots are particular types of weights adapted to the adjoint representation. Okay, so the root lattice is the Z span, so all integer linear combinations of the simple roots. And this is certainly going to be a subset of the weight lattice. Okay. The weight lattice is strictly finer than the root lattice. Okay. Basically because well, we know we could write out any root as a integer linear combination, since each alpha I is a Z linear combination of the lambda basis. Okay. So let me give you a picture. It's over here. I cheated a little bit. Let's see. Good. Okay, so here's the picture on the a little bit more. Okay, so on the left side here, what you see is the weight lattice. Okay, so here's alpha 1. Okay, here's alpha 2. Okay, alpha 1 plus alpha 2, I guess, is this one right over here. Sorry, this one right here. Yep. If you plot lambda 1, it's right there, and plot lambda 2 is right there. So there's that collinearity. Okay. But right, definition, the weight lattice, you take lambda 1 and lambda 2 as your basic starting vectors to start out with, and just take all possible Z linear combinations. So you get all these dots that appear over here. For the root lattice, we start out with alpha 1 and alpha 2 and take their Z linear combinations. Okay, so this lattice will, it's a subset of this lattice over here. Okay, this is finer. Okay. But the conclusion, the important conclusion from the discussion above is that only integral weights can occur in I. Okay, as in only these weights lying on the weight lattice can possibly occur in any possible representation of SL3. Okay. For a given representation, we can draw its weight diagram. So let's see what these look like for standard, dual standard, and adjoint. Okay. So what you see here is the standard rep, dual standard rep, and the adjoint representation. Okay. I'm going to label some of these. So here's lambda 1, which is the same thing as epsilon 1. Here's minus lambda 1 plus lambda 2. So that's epsilon 2. And here's minus lambda 2, which is epsilon 3. Yeah, so that exercise that I suggested before about, verifying that the epsilons are written in terms of the lambdas in this manner, we can do that now that we have the dictionary between the alphas and the lambdas, right? So we have, I guess, over here. Okay, so you have these. Alpha 1 is epsilon 1 minus epsilon 2. Alpha 2 is epsilon 2 minus epsilon 3. So you can do some linear combinations and figure this out. Okay, good exercise. Okay, so let's go to the dual standard. Okay, so what do we have here? Okay, so we have, this is lambda 2, which is minus epsilon 3. This is, I guess, minus lambda 1, okay, which is epsilon 1. And this is lambda 1 minus lambda 2, which is minus epsilon 2. Sorry, I made a mistake. Minus epsilon 1. Okay, so the negatives of the standard representation weights. In the adjoint case, here's lambda 1 plus lambda 2. And then, well, of course, this is the zero weight. Okay. But I'm gonna do it right now. Yeah, let me not do this wrong. Actually. I know the answer up to a transpose, up to swapping. So let me not. It's an exercise for you guys to fill this in. Okay. Okay. So that's what things look in specific representations, right? This is a three-dimensional representation, eight-dimensional representation. Okay. This is basically, you could call it a weight space decomposition, and these are the corresponding weights for each of these representations. Okay, but now we have to define, again, an analogy with SL2. What do we mean by highest? Okay, and what we're heading towards is the so-called theorem of highest weight. Okay, if we understand this for SL3, for the other semi-simples, it's basically the same. Okay, so we're in a two-dimensional vector space. What do we mean by highest? I mean, a two-dimensional vector space doesn't have a natural ordering, right? Unlike a line, which you could identify with R, there is a natural ordering, a total ordering. Okay, so here instead, the choice of simple root basis induces a so-called partial ordering, okay, that we could use to define a notion of highest. Partial ordering, and we'll talk about dominant weights. Okay, so definition. Okay, so it's going to be a partial order in the sense that, like, not all elements are comparable. You can't say for all elements, we could say that, one is bigger than or equal to another. You can't always compare elements. Okay. So, so let mu and lambda be elements of H star. Let these be weights of a rep pi. We're going to declare that one is bigger than or equal to another if and only if lambda minus mu is greater than or equal to 0. But what does that mean? So let's take this weight and write it out with respect to the simple roots. Okay, not the fundamental weights, but the simple roots. Okay, if and only if when I write this out, then these coefficients are all greater than or equal to 0. Okay. And then we're going to say that, whoops. We're going to say lambda is highest weight if lambda is greater than or equal to mu for all weights mu of this representation. Okay, reasonable definition of highest weight. Okay, so remark, as I was saying, this is a partial ordering. So not a total ordering. Not all elements are comparable. So for example, for alpha 1 and alpha 2, we have neither alpha 1 greater than or equal to alpha 2, nor alpha 2 greater than or equal to alpha 1. Okay. Why? Because if you had this, that would mean that alpha 1 minus alpha 2, since this is not true, and this is not true. Okay. Right. What am I supposed to do if I want to compare it to compare two things? I take the difference, so that's this, right? I write that out in a simple root basis, and these coefficients should be non-negative, but the coefficients here are 1 and minus 1. Okay, so it doesn't make sense to, so these are not true. So you cannot compare alpha 1. You can't say that 1 is bigger than or equal to the other. Okay, so what can we say? So for the again, let's go back to the examples. So for standard rep, with weights epsilon 1, epsilon 2, and epsilon 3. Okay. Oops, sorry. Yep. Thank you. Yep. For the standard representation with weights epsilon 1, epsilon 2, epsilon 3, here we can now use this partial ordering. We can say that epsilon 1 is greater than or equal to epsilon 2 is greater than or equal to epsilon 3. Okay, so why? Well, to show the first one, then you're supposed to take the difference. So epsilon 1 minus epsilon 2, but that's just alpha 1, right? So here, when I write out this result in terms of the alpha 1, alpha 2 basis, it's 1 times alpha 2 plus 0 times alpha 2. Both of those coefficients, 1 and 0, are non-negative. Okay. Epsilon 2 minus alpha 3. Epsilon 3 is alpha 2. Okay. So again, yeah, so I guess I could say this is true. Okay, so this means that the coefficients are non-negative in the alpha basis. Yes, it's transitive. Think about it. Yeah, think about the linear combination.
maximum?
For partial or yeah, so that's the theorem about partial orders, that there always exists maximal elements. You don't always have it unique, right? You could have different chains of this being greater than or equal to another. So you might get a maximal element here, maximal up there.
For the definition, the mu is maximum if it is comparable with everything.
That's right. So there is a non-trivial theorem there.
Oh.
Yeah. Excellent. Yeah. Okay, so let's list now. Weights of reps of considered thus far. Okay, so standard, dual standard, and adjoint. Okay, actually, I basically did this. Epsilon 1 is lambda 1, epsilon 2 is lambda 1 minus lambda 1 plus lambda 2, epsilon 3 minus lambda 2. Okay, here lambda 2, and then lambda 1 minus lambda 2, and minus lambda 1. Adjoint, lambda 1 plus lambda 2 minus lambda 1 plus 2 lambda 2, 2 lambda 1 minus lambda 2. You have 0 with multiplicity 2. 2 lambda 1 minus 2 lambda 1 plus lambda 2, lambda 1 minus 2 lambda 2, and lastly minus lambda 1 minus lambda 2. Okay, and well, this is our highest, this is our highest, this is our highest. Okay, seems like there's a lot of information below the highest. We're going to see tomorrow how to generate all of this information in a very simple manner. Okay, so everything is recoverable from the highest one. Okay, just like it was for the SL2 case. Okay, let's give a definition. So we talked about which representations can appear in which weights can appear in representations. They have to be integral weights. So we just need to focus on the weight lattice. The next question you can ask are which such integral weights can appear as highest weights. Okay. So let me formulate a definition, give you a picture, and then we'll formulate the theorem of highest weight. And that'll be good for today. Okay, so let mu. Oh yeah, I formulated this all for SL2, where I just have two simple roots. But yeah, similar definition for other cases where you have more. Just your coefficients should be, with respect to the simple root basis, should be non-negative. Okay, so let mu be in H star. Well, actually, before I formulate the definition, what do you notice about these weights that I've put in orange? The coefficients are all non-negative with respect to this fundamental weight basis. Okay, so that's what's this what we're going to formulate here. Then mu is dominant if these Ri's are real non-negative for all I. The set of all dominant weights. Okay. Actually, maybe you want to restrict to the real slice. Yeah. Okay. Maybe. Okay. Let me not put it in right now. This is something called the fundamental vial chamber. Okay. So here's a picture. Oops. Just keep it like that. Okay, so here's 0, here's lambda 1, lambda 2. Okay. And basically anything in this area here is a linear combination of lambda 1 and lambda 2 with those coefficients being non-negative. Okay. Actually, I think I should put let's see. So let's restrict to the real slice. Okay. Okay, so yeah, so this is the fundamental chamber. Anything in here is called a dominant element. Okay. Of course, to consider representations, we should stick to working on the weight lattice. So points here, 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 etc. These are potential candidates for being highest weights for representations. Okay, so necessarily these are going to be in there, but conversely, you could ask, hey, given one of these integral dominant weights, does there exist a representation with that appearing as its highest weight? Okay, and the answer is yes. Okay, so that's the theorem of the highest weight, which I'll formulate next. Okay, so first of all, notation: a lambda 1 plus b lambda 2. Okay, this weight is sometimes encoded on a Dinkin diagram. Okay, with these coefficients being put over the corresponding nodes. Okay, so for example, highest weights of reps considered. Okay, so standard, dual standard, adjunct. Okay, so this is 1, 0, 0, 1, 1, 1. And now here's the theorem of highest weight. Okay, I'll formulate it for SL3 right now, but basically every statement generalizes very nicely. So first of all, every irreducible representation is the direct sum of its weight spaces. Okay, so this is like root space decomposition, right? But for weights. Okay. Sorry, yeah, irreducible for irreps. And every irrep has a unique highest weight. Mu. That is dominant integral. Okay, so it lies on that weight lattice, and it lies in that fundamental chamber. Two irreps with the same highest weight are isomorphic. Okay. As in, they're completely, so these irreps are completely classified by this data of the dominant integral weight. Okay, so this is the analog in the for the SL2 case. There it was M, a non-negative integer classifying the representation. You know what those representations are, you could realize them as these SMC2 representations, nth symmetric power of standard representations. Finally, the realizability question. Okay, so for all dominant integral weights, there exists an irrep with highest weight mu. Okay, so let me just now summarize. SO3 irreps modulo isomorphism are in one-to-one correspondence with weights that are integral dominant. Okay. And I'll also write these just in analogy with the notation used for SL2. We'll write this V A lambda 1, B lambda 2 for the corresponding representations. Okay, so these, we can construct all these representations concretely. We'll see some details of that next time. But yeah, they're classified by these integral dominant weights as highest weights. Okay. Yep.
So the point two, every irrep has a unique highest weight mu that is dominant integral.
Yep.
Does it have a unique highest weight and it's dominant integral? Or if we assume it's dominant integral, then you have a unique highest weight.
Every irrep has a unique highest weight. Let's put and it is dominant integral. Yeah. Yep. Good question. Any other questions there?